electron transfer model for semiconducting field. And semiconducting materials have been in great interest for photovoltaic technologies. Electronics and semiconductor engineers rely on MATLAB to develop smaller and more efficient devices. So in this project, there is a little endeavor to understand how a packet moves through the interface of the p-n junction. So we use MATLAB to simulate a series of energy well for wavepacket in the p-n junction, and we solve the Schrodinger equation using evolution operator. The bold shows in bold letter, and to run the simulation, we centered the wavepacket at 30, and the wavepacket has initial kinetic energy 0.42 hertz, and the number of points in the simulation cell is 200, and the difference between every two point is 0.4. So this shows in a x-axis. All units are in AU, atomic units. So this shows the results after running the MATLAB codes. The left corner, right upper corner shows the probability of electron transfer over time. So this curve shows that it takes the stepwise increases because of the repetitive cycle of the wavepacket in the simulation cell. And right corner shows how the probability changes with the initial kinetic energy of the wavepacket. So kinetic energy converted into temperature, then we plot this graph. So it shows that initially the probability increases with the temperature, but at a certain time it decreases. And if you see the temperature is too high, it is 5,000, and here it's like a temperature of the sun surface, so it is unrealistic. And the left corner, lower corner graph shows how the rate transfer constant changes with the temperature or kinetic energy. And right corner, lower corner shows for this we actually run the wavepacket from the higher potential to lower potential to higher potential to lower potential, lower potential to higher potential. This is the difference. Opposite. These are two opposite. And here is the videos for my project. The wavepacket moves through the So at conclusion, we can say that electron transfer depends on initial kinetic energy and position from where its journey. As the kinetic energy exceeds the wave energy, the wavepacket can eject itself completely from the energy well and then loops around the boundary. And the simulation is done at a high temperature, so it is not realistic. Thank you.
Okay, let's thank Hossan. And we do have a question from Jeff.
If you wanted to make your model more realistic with lower temperatures, how would you go about doing that? Could you lower the difference between the wells?
Oh, actually, I change. So the temperature is kinetic energy is converting into temperature. So actually, run several times. Also the kinetic energy depends on the momentum. And when I run the momentum, keeping 0.0, it's actually done 0.1 atomic unit for the momentum. But when I run it less than 0.04, it actually doesn't work.
I'm just wondering if you maybe create a smaller barrier between the P and the N sides, and then use a lower temperature to be able to tunnel through it.
Could you please repeat?
If you had a really small barrier between the P and the N sides of your model,
Yeah.
then it might be possible to use a much lower temperature to be able to tunnel through it.
Yeah, I think so.
Okay, if there are no more questions, let's thank Hossan once again. And the next presentation is to some